All right, and we're on.
So, good afternoon.
Good afternoon.
I have, this is, my time here has just been so selfish for myself in a lot of ways, right? I've had the opportunity to talk about things that I'm super passionate about, right? So one of them you heard about earlier, and this is something else that I was passionate about. And what I found is someone who may rival me in my passion for this subject. At the beginning of the project, there was some concern about putting people in groups, right? And so when it came time and I presented two topics to talk about, then it turned out that Trajan might be in a group by himself, a group of one. And what you have found during the time here with him, I think, and with this project, is that if anyone was uniquely qualified to be an individual, it was certainly him. It has been an honor to work with you on this and to follow your lead in your investigation of this. So I want to say thank you, and let's enjoy.
Well, thank you, Dr. Winger. I can say that although I did have to work on my own, it was definitely worth it to work on this particular project. So I just want to say I appreciate, wait, am I in the chat? Okay, I appreciate having spent the past 8 weeks under the tutelage of Dr. Eris Winger on how we evaluated this school policy using math. All right. Yeah.
You need to go closer.
Oh,
There you go.
Okay. So before we begin, I just want to explain some of the motivation behind our project. So Dr. Winger was sitting in on a conference call during a Board of Ed conference, right?
I was at a conference call.
Okay, you were at a conference call. And he overheard about a school disciplinary policy being used at Pittsburgh, Arlington, which they refer to as the Pittsburgh Arlington leveling system, which sorts their students into 3 different categories based on their attendance and their willingness to obey instructions, behaviors like that. So what happens is, every 2 weeks, the teachers convene and discuss which students are going to go into which categories. The thing that stood out to us was that students were required to wear a colored armband that signifies their color. This prompted further investigation into the outcomes of such a policy.
A tad closer. Just a tad. There you go.
All right. So again, I just want to outline some of the things we'll be talking throughout this presentation. First, we'll go over what Markov chains are and how they work. Then we'll talk about how they apply to Pittsburgh Arlington's leveling policy. After that, we'll talk about some of the constraints that we put on our model in order to make our calculations possible. And then we'll talk about how we actually went about those calculations. After that, we'll talk about our findings and what we suggest for the future.
Maybe try and stand on the other side, like that could be better.
I mean, then I'm blocking things though.
Okay, I can see.
Yeah, you're good. You're good. Just send some of it inside.
Alright, well in that case I'm going to... Alright, so let's start off with how Markov chains actually work. So basically, if you have a system where a bunch of particles are moving through different states, one way of looking at how those behave is to model it as a Markov chain. So we say that a process is essentially a Markov chain if the probability of a particle going from one state I to another state j only depends on their current state that they're in. Doesn't matter how long they've been there, doesn't matter where they were in the past, doesn't matter how many particles are there. All that matters is that they're here now, and you can predict the probability of where they're going to go next. So it's convenient to assemble these P sub ij's into a matrix such as this, such that the ith row, jth column element is P sub ij. And you'll see why we do this in the next few slides. So one thing that you should notice is that the row sums have to add up to 1. That is, if I'm standing in state 1, then my probability of staying in state 1, then going to 2, or going to 3, or going to 4, or going up until state k, they should all add up to 1. And the same could be said for all of the other k states. So here I have an example of a Markov chain of the matrix of a Markov chain of 3 states. And it's usually convenient to visualize them as a diagram. So you see, if I'm in state 1, then I have a 21% chance of staying there. I have a 68% chance of going to state 2, and an 11% chance of going to state 3. And I can say similar things about the probability of going from state 2 to somewhere else, or from state 3 to somewhere else. Okay. So suppose at the start of the time that I'm looking at this Markov chain, my particles are distributed such that there's this much in state 1, this much in state 2, blah, et cetera, this much in state k, which I store in this vector x naught. After one step in the Markov chain, after all the particles have moved according to their probabilities, I just get the next step, next distribution vector x1 by multiplying x naught by my matrix P. Similarly, if I want step 2, I just multiply it again, x3 again, multiply it again. And in general, if I want to find the distribution of particles n steps later in time, I just multiply it by the nth power of the transition matrix. So for some Markov chains, what I see is that for any initial distribution x naught, if I evolve my Markov chain long enough, I should notice that the particles tend to converge to the stationary distribution we'll call pi. And this is for any initial distribution. Hopefully that'll be clarified on the next slide. So this happens if P is regular. And we say that P is regular if for some k along in the chain, PK attains all positive entries. So here, if we go back to the example Markov chain I had 2 slides earlier, if this is the transition matrix, and if I evolve this Markov chain long enough, what I should notice is that I have about 14% of my particles in state 1, 25% in state 2, and about 60% in state 3. I'll talk about how we calculate stationary distributions in a couple of slides. So now that you know how Markov chains kind of operate, we will apply the properties of Markov chains to the leveling policy being used in Pittsburgh, Arlington. In this case, the particles are going to be the students, and the states are going to be the colored categories, red, yellow, and green. So the transition matrix is therefore going to have this form with the probability of red going to red going to yellow, red going to green, and so on for all the other states. The ending distribution, again, we're just going to denote as pi, and it's going to be pi sub r, pi sub y, and pi sub g. Now, for the purposes of investigating the outcomes of this distribution, we're concerned about the long-run fraction of students in this red state, pi sub r. But we have a problem. We don't know what these transition probabilities are. And first of all, it's not like the school even reports what these probabilities are. And even if they did, it's not like they would make that public information. So it's up to us to find out some reasonable values of what they might be. Well, to help us do that, we're going to make some simplifying assumptions about how these transition probabilities might behave. So our first assumption is that the probability of going up, that is going from red to yellow or from yellow to green, they're going to be equal, and we're going to denote that as the upwards mobility rate. Similarly, the probability of going from yellow to green, or I'm sorry, from green to yellow or from yellow to red, the probability of going down, we're going to refer to that as the downward mobility rate. And next we're going to assume that the probability of red staying in red and the probability of green staying in green, those are going to be denoted by R and G respectively for red retention rate and green retention rate. So now we just need to worry about what these diagonal entries are going to be. Well, like I said earlier, the row sums have to add up to 1. So we know that they're just going to be 1 minus what the other two are. So now I want this matrix, or we hope that this matrix is regular. That way we can find what the stationary distribution is. Well, in order for it to be regular, we need that all of these things have to be positive, and that r plus u needs to be less than 1, so that this can be positive. Similarly, this needs to be positive, and this needs to be positive, which happens if these two things happen. So, okay, I put some other constraints on there, but I still don't really know what they are. Fortunately, what will mathematicians do in this predicament? Well, first off, let's just talk about the stationary distribution before we answer that question. So, it should make sense that if pi is a stationary distribution, it shouldn't change if I evolve it one more step in time. That is, if I multiply it by p, it should just remain the same. You should recognize that this means that pi is just an eigenvector of the matrix P with eigenvalue 1. And then solving for it is just a linear algebra problem. So since the elements in pi have to add up to 1, that means that it can be uniquely solved. And if you use a computer algebra system, if this is our matrix, then this is what pi sub r will be. It's a very beautiful formula, but we'll get more on that later. Okay, so since we still don't know what r, g, u, and d are, what mathematicians will do in this case is we're just going to assume that they're random variables, and then it's just a question of deciding their distribution. Well, a lot of things in nature tend to have normal distributions, but again, since r, g, u, and d are transition probabilities, they have to be between 0 and 1, which means we're going to assume that they have a truncated normal distribution, one of which is pictured down here. So after that, it's just a matter of finding out what appropriate values of mu, the mean, and sigma, the standard deviation, should be. So in order to tackle the problem of finding the mu's, we hypothesized 9 different schools. And to help us hypothesize these 9 different schools, if you remember those constraints earlier about r, g, u, and d having to be positive, and u plus r having to be less than 1, all that, I let the set of all possible combinations of r, g, u, and d, I considered that S. So if S is the set of all points that fit these constraints, essentially what I did to find out appropriate values of all the mu's is to give these different values of 0, 0.5, or 1, such that this point lied in S. Hopefully that will be clarified on the next slide with a few examples. So for example, suppose I was to assume that the red retention rate was close to 1 and the green retention rate was close to 1, and that the upwards and downwards mobility rates were close to 0. Well, that would mean that my distribution of students doesn't change a lot over time. And that is made clear because the transition matrix it induces is just the identity matrix. Now similarly, if I were to assume that the red retention rate is really low, the green retention rate is really high, and the upwards mobility rate is really high, that'd be pretty characteristic of an exemplary school, and this is the transition matrix that this point would induce. Okay, so doing this for all different possible values of the mu's, I was able to come up with these 9 different schools, which I'm sure you definitely want to hear the gory details about how they behave, but in the interest of time, I'll spare you that. So with that in mind, we now want to estimate the probability that pi r is greater than some epsilon, that this probability is greater than some p head for some small epsilon and some high p head. So essentially, we're taking the probability that our red category in the end is of some significant size with high probability. Okay, So since R, G, U, and D were random variables, and pi sub r was a function of them, you actually saw that it was a pretty complicated function. That means that pi sub r is itself a random variable, and we calculate the probability that it's greater than some epsilon by integrating the joint distribution of R, G, U, and D over the region T sub epsilon, where T sub epsilon is the region in S where pi r is greater than epsilon. So show of hands in this room, who would feel like integrating this, either by hand or by computer? Okay, getting a lot of head nods, that's what I thought. And I didn't feel like doing that either. Fortunately, there is a helpful tool that allows us to approximate integrals with that are in multiple dimensions and have complicated boundary conditions. So we refer to this process as Monte Carlo approximation. And here's the general breakdown. Suppose we have this region in Rn that we're trying to integrate. We want to draw a box that contains the entire region, throw many, many points in that box, see how many points land in the region we're trying to integrate, and then compare the ratios. If all works out, then the ratio of then the proportion of points that fall inside the region of interest should approximate the ratio of the volume of the region to the volume of the box. So here's a simple two-dimensional example. If I have a circle and I draw a square that circumscribes it, and if I throw a whole bunch of points in it, the number of points in this circle, or the proportion of points in this circle, should approximate pi over 4. So we use this to essentially estimate the integral on the previous slide. Okay, so let's talk about how we're applying it here. So here we're going to set epsilon equal to 0.1. That is, we're looking at the probability that at least 10% of the student body in the long run ends up in the red category. So our region of interest is therefore going to be pi sub r being greater than 0.1. We'll draw a unit box around this region, T sub 0.1. And then we're going to throw random points in that box, which have distributions according to the correct school. And what this will give us is the probability that pi sub r is greater than 0.1, given that these parameters fall in our region S. We're going to do this for all 9 schools. So I talked about how we found the mu's. Now it's time to discuss how we found the sigmas. Well, we kind of didn't, but we made some good guesses about what it might be. So since all of these random variables were bounded from 0 to 1, that means that their standard deviation should be at most 1/2. So what we decided to do was test 8 different values equally spaced between 0 and 1/2, and use that to approximate this probability that pi sub r was greater than 0.1. So this graph plots the different values of sigma on the x-axis and the different probabilities of having 10% of the student body in red category on the y. And then these different lines represent the different schools. So 9 different schools, but 4 different lines. Actually, most of the lines are behind here. So as you can see by the graph, for most of these schools, we have a pretty high probability of having at least 10% of students in the red category in the long run. The only schools that kind of behave okay are the rehabilitative and exemplary schools, which we'll talk about that later. So essentially what I have here just kind of sums up everything I just said. Just for kooks and giggles, the exemplary school I already kind of described. A rehabilitative school has a green retention rate close to 1, but the upwards and downwards mobility rates are closer to 0. So let's go back to the graph. These were the schools that even had the probability of doing well, had a low probability. But if we just shift sigma a small amount, then we're already up to a 30% chance of that happening. And then it only increases from there. So if we want this to happen, we essentially have to make sure that our parameters R, G, U, and D are fairly rigid and not subject to a lot of variation. So, given all that, we think that this policy is inadvisable in its current state. All right, so I just kind of want to recap everything we went through. So we modeled the Pittsburgh-Arlington leveling system as a Markov chain. We showed that the red category in the long run has a high probability of comprising 10% of the student body for most schools, and even in the schools that it didn't. Well, there are certain conditions under which that must be true. So given these two things, our best piece of advice for now is to at least not have students wear the armbands. Right. So of course, there's still a lot of work to do before making any fast and fixed decisions about this policy. This Markov chain that we used was just one example of how to model this process. Even if within the realm of Markov chains, there are many other ways. Some that, if this project continues in the future, which it definitely will, right, Dr. Winger?
Yes.
Mm-hmm. We'll definitely look into some different models. And also, we'll try to investigate the effect of other school policies might have on these values of R, G, U, and D. All right. So in my remaining time, I would like to make some acknowledgments. I want to shout out to the NSA for funding the SWAMI program for 2018. Thanks to Carnegie Mellon University for hosting all of us. Thanks to the program director, Deborah Brandon, for electing all of us to be here and pursue this important research. Thanks to my advisor, Dr. Eris Winger, for making this project possible and bringing it to the light. And thanks to our assistant project director, Jessica De Silva, for answering our questions and all. Thanks to everybody who came out today, and thanks to Hutam Betawal, for letting me borrow his blazer. So, any questions? Isaac.
So, not to put you on the spot or anything, but
put me on the spot, right.
What, do you have any idea of a proposed alternative, like to reward good behavior and disincentivize bad behavior,
Well, when I was reading through the policy handbook, the policy essentially stated that being in the green category would result in certain privileges, and being in the red category would result in loss of those privileges. I don't remember off the top of my head if those privileges were made clear, but to my best memory, they really weren't. And that's more of a policy and school issue rather than a mathematical issue.
Mm-hmm.
Brady?
Do you know if any psychological studies have been done on this issue or on this particular policy? On how it affects the kids?
I don't know about psychologically. However, I actually did some work similar to this, not in math, but just kind of in a sociological way, about 4 years ago. And we investigated how restorative practices affected school suspension rates and graduation rates. And password, please.
Yeah.
All right. And schools that implemented restorative justice practices tended to have lower suspension rates and higher rates of graduation. So I'm not telling Pittsburgh, Arlington to automatically take up these restorative practices. It'd be cool if they did, but we still have more work to do before making any decisions about that.
Thank you.
Thank you.
All right.